Welcome to a new test and teardown video. This time it's a power supply. This looks like a double, but it's actually a triple power supply. And it's a Digimess Concept Series DC power supply HY3003-3. So that is 30 volts, 3 amps and 3 outputs. And they go under quite a lot of different names. This is a very much cloned China design. So you could probably see a lot of different like brands. They change these little plastic stickers here and they change this sticker here behind all the knobs. But other than that, it's exactly the same inside and outside. There's another one that's called Mastech, and I've been Googling a little bit around to find some schematics, and I can't find exactly the schematic for this particular model, the 30 volts and 3 amps and 3 outputs. But I can find the 10 amps and the 20 amps versions, and I believe they use like 99% of all the intelligence once again. And I got 2 of them, and they're in for repair. And the fun thing is they both got exactly the same fault. So I expect this video to be a little repair video, and it will probably show that there's a weak part in the design, because this one has a defect current limiter. So let's look at the internal parts of this fantastic power supply. We are not surprised to see 2 circuit boards for the 2 main power supplies. Here is of course one, and here is the other one, because it's 2 identical isolated main power supplies, and it's quite heavy. There's a nice toroid transformer with tons of outputs, as you can see here. The little 5-volt supply is down there, and this is the one that handles this little 5-volt 3 amp additional output. So it's really good for your experiments. You can run everything on fixed 5-volt here and do your variable experiments on the 2 main supplies. So that board there, since it's a 3 amp supply, obviously the rectifier, I don't know how easy that is to see, but it's a big hefty one, and it is of course connected down to the bottom chassis for good thermal design, so that I am happy about. We see this little, I don't know, can you see this connector here with the red, blue, black wires? They go to that transistor right there, and there's of course a nice little IC regulator and all that fancy stuff. And see something cool about the thermal design here. So the 2 main heat sinks outside, they're outside located, so this is really good for good thermal design. And this little additional power supply here connects thermally to, of course, chassis, and then to the 2 main heat sinks. So I think this is probably the best of what they could have done with this type of design. So not bad at all. I took away one of the protective covers here on the back. There's just one little screw here, and then it slides up, so we can see the transistors. And we got 2 N3055s and room for 1 more. And they are of course using the heat sinks, the cases, every part here is a reuse between all their different models. If you look here, you can see of course the circuit board also fits 1 more transistor, and there's room for 1 more wire here in case you have all 3 transistors mounted. So since this one is a dual 3 amps, you only need 2 and 2 transistors. But you can also have this power supply in a single 10 amp or a single 20 amp version. And that will also be the schematics that I show. This is where everything is populated. Then you can, of course, imagine less and less high power parts will be mounted in the weaker and weaker versions you got. I added a little note to myself because I got 2 of them. So I need to go back and forward here and do a little bit of measurements. So the front readout systems, we are of course not surprised to see 2 individual readout systems with all their own, see, the rectifiers and all that stuff, using some windings from the transformer to handle all that. And you need to select from the front if you want to see here volts or amps readout on both of them. So that is a little bit, I mean, I really prefer to see a voltage and current at the same time, but that is just a way that they try to save cost a little bit, and also room on the front. Got some pretty big 7 segments, so you can imagine it would have been a little bit difficult for them to put in double the number or make them half size or something like that. So I don't think there is something wrong with the readouts, so I'm not going to dig super much into this. I believe the trimmers we can see here is of course for readout calibration. It is using the emitter resistors as the sense resistor system. So obviously those are not the most super duper tip top types, but I mean, it's not that bad either, right? So you see we got 2 of them that is 0.82 ohms each, and they each carry the 1.5 amps. So what is that? About 1 volt each of dropout for your full scale readout. What else can I see? This is of course again the same circuit board they use for all the different models. And you will see we can fit in some more relays if they have more tappings. The higher amp power supplies, they use more tappings. So that is a good idea. This way they keep the voltage over the transistors lower, the more steps you can have, right? But here we have only 2 relays in this model. That means also we have a few of the transistors to select relays. They are not mounted. So this op amp there and the resistors and all that stuff we see around here, that is this area handles the relay switching. That systems simply measure the output voltage and switch the relays according to only the output voltage. And what we see here is the voltage regulation and the current regulation. 2 individual single op amps, and this one is the TL431 2.5 volt reference. We've got of course a little bit of trimmer. Those trimmers, they handle full scale and 0 on the potentiometers on the front, so that is something I also want to double check. But I think I will try and power it up and see what is going on. Yes, I can also say that the 2 power NPN transistors, yes, they go here, and then this is the driver for those, and then this is a little pre-driver for this one. So it's just Darlington all the way, right? Emitter followers, so it was super high current gain. And here we see the little Zener diode and pull-up resistor and this diode that goes to the driver transistor, and then it goes to the op amps, obviously. I think I should try and show the schematic. This schematic is for the, I think this is the 20 amp unit. You see in the middle all 6 output transistors mounted. So that reveals that we have the big and powerful model. If you look at the ground symbols on the schematic, they will maybe confuse you a little bit in the beginning, but I will now add some circles around all these, and I will show you they are connected to the positive output. And the reason for adding a ground symbol on the positive output voltage, that is because they use this as a as a reference to all the voltages that is written in the schematic. So this way you can easier debug and measure the different voltages. All you have to do is use the positive output as your reference point. And yeah, that is what was most annoying to begin with. My model is the only 3 amp version, so that is why I don't have this winding to the left, the middle winding that generates an auxiliary voltage that is put on top of the primary voltage. This one is the supply that drives the pre-driver. So there is another pre-driver, and for that one you need quite a lot of drive current to drive all 6 output transistors in parallel. And this is why they added an extra little very low voltage winding. And the idea is that instead of taking the power from the 12 volt regulator you see at the top left, and this is what they do in the lower current models. And so that is the difference mainly between the low current and the high current models of this one. Otherwise the rest of the circuit is exactly the same. And yeah, to the right you see the bottom right part, you see the 3 op amps. They of course only handles the relays. In my model I have of course only 2 relays mounted, but in the schematic you see all 3. And of course there will be some different resistor values depending on output voltages and how many relays you have and how many steps and all that kind of stuff. And that should be explained somewhere else, but I don't have that table with all the different values explained. In the middle bottom part we see the 2 op amps that is used for current and voltage regulation. The bottom one is the voltage regulation op amp, and you have different potentiometers for voltage adjustments and current adjustments. They are marked with dotted lines, and this is of course because they use they reuse this board for many different versions, and in some versions they have 2 potentiometers in series for fine and coarse adjustments. But in mine I do not have this, so it's just 1 potentiometer on each side. And then we see the output from the 2 op amps is sort of gated together using the 2 LEDs, and those LEDs are the ones we have at the front that shows if it is in current or voltage mode. And the current to those 2 LEDs is a sort of a constant current supply, because it is a constant voltage above our output voltage. It comes from the 12 volt regulated, and it goes via a resistor and a zener, and this way it generates a current into the pre-driver and the driver transistors for the output stage. So that is more or less how this fantastic thing works. I think there's a very good chance I can just front plate test this and see directly what is the problem. See, what I will do here is I crank up the both current settings maximum. Okay, voltage down, and these 2 are out. So that means we have now 2 individual power supplies, right? See what's happening. If I take the 2 voltages all the way up, this one is the one that works. I mean, it actually do climb, but this is really weird, right? So there's no drive to the output stage. Okay? So all you have to do is wait. and then it's probably gonna get there, right? Let's try the other way around. What happens if I turn both of the outputs all the way down very, very fast? What is then going to happen, okay? And again, this one looks weird, right? So I feel there's just a missing connection somewhere. Isn't that amazing? There's something that is not connected correctly. And the voltage, see the clicks? So this one happens around 10. Around here, right? Let's check the other side. So I just left this at on. Okay, so this is more or less the same point, and it looks like it is in regulation. So here comes really the funny thing. Let's try current regulation here, right? So this is of course at full maximum, and it's unloaded. See, and now it goes to constant current mode. So when this one goes all the way down, the reference voltage to those op amps goes below what it is measuring. And this is a wanted thing. You want this to go to 0. Let's see if the OK side is also doing this. So that seems to be perfectly fine. We have the 0 points. I believe we have another problem as well. So now I've connected an external voltmeter to see what is actually going on here. Because do you really trust the built-in voltmeters? Let's see if we do that. Ooh, oh dear, what is that? So that means the internal voltmeter here is not... Oh, here it is. No, it is not. Oh, here. So here is the... Here is the what? What? Okay, this one is the most buggy at the moment. And this explains... Okay, now I have repaired that little bug. Let's see if it's the same with the current. Haha, that is interesting. Is it really only that one? That could be fun. After a lot of massage on those switches and contact 61, I now have a nice volt readout that is responding nice and fine to the actual value of the output terminals. How about that? And I also got an amp meter that goes to almost 0 on both sides, and they were absolutely not responding to both sides. I had about 2 amps of offset, so I thought we had a defect amp meter, but it's only the switches. So let's crank up the output current like that and then turn on my load. So here is 2 amps exactly on my load, and it goes 2 amps. And then I can of course try and take the, see, that is the current set point. And now I can of course dial it all the way down. Doing. And the LEDs and all that works perfectly fine. So I mean, so far the only fault I found was that switch. Isn't that a little bit amazing? There's also nothing I can do about its calibrations. It really reads out to the last digit. We only got 1 decimal, right? So here is 10.0 on that side. Let's see, those are individual. And the other one. I think I'm quite happy about this, right? Another little thing to fix while I am at it. I mean, this tiny little mark here, I don't know if you can see this. This one is a little bit different from all the others. If you take a little permanent marker and put a line here in the middle, now it's easier to see what you're doing. And please don't push the knobs all the way in so it scratches on the front. I mean, leave a 1/4 millimeter so you don't hear this annoying scratchy sound. I really hate when people do that. So now when everything works in this power supply, I'm doing a little bit more visual inspections and see what I can find. And can you see what's happening here in the middle of the picture? This connector here. This one here, right? Can you see the two little metal parts, especially the one in the middle? I believe if I take this wire here and pull a little bit, it is actually all the way into the click, but you see the red one is all the way correctly down. And I just checked all the others, as you can see there. See, oh, I don't know. I don't like it when they're that high up. That is probably not how it should be. I checked the other one on the other channel. See? And that one haven't got this problem. So somebody's been pulling out this cable too hard, I guess. Other minor issues to mention. The cables from the left heatsink goes directly through the mains voltage selector. I don't know if you can see this, but the way that they cut those wires, they're quite sharp, some of them. So I took a little piece of this extra plastic isolation from here, where it doesn't really help a lot, and I put it here on these wires, and I tried to bend them a little bit further away so that we will not have a nasty quality issue to mains voltage. And there's actually one more little dumb idea here. What they're doing is they put solder on top of the traces, as you can see here, and then they put the screws and nuts and all that in here. So that means you have a pressure onto solder, and that will float very, very slowly, but over some years you will not have the same and the correct pressure on these points to the collector of your transistors. So I think you should try and tighten these screws just a tiny little bit every 10 years or something like that, right? And I of course tried to tighten the screws here in the one that I have open, and they were really, really loose. Let me try and see if I can demonstrate this. Let's try and open the other one. So let's see if there's any way I can demonstrate this. I will take a screwdriver like this, and then I will see if I can. No, it's not. They're not that loose. Well, of course, if I take it like this, it doesn't really feel that bad over here. Okay, it's not like they're falling out all by themselves, as it were in the other one. But definitely I want to give it a half a round. Oh, not that one. So, okay, it's a little bit different how much solder they added. The thicker layer, the worse, obviously. So one last funny thing. There's of course also a 5-volt fixed 3 amp output. So let's try and see what that one can do. So they say 3 amps, right? So this is the specifications. 4 amps, 5 amps, hoppa. So that means there's no current limit. So here is the little 5-volt so-called 3 amp power supply, and there is no current sense, protection, or anything at all in this design, and there isn't even a melting fuse in the supply line, the AC line, the DC line. No. So if you short these, you're probably going to damage something here, right? Oh, that is not good. A lab supply without protection. That is a fail. And now I got the other one, and I can reveal it is the same problem with those switches. But the first thing I wanted to show you here is just absolutely funny. So that will be the 5 volt 3 amp output. All right, let's play with that one alone. So 1 amp, 2, 3. So this is the normal low, right? Let's give it 4 and let's try 5. Oh, there's a fold back. So there is, of course, a short circuit over load protection. And see, if I go all the way down to 0, it comes back alive. Perfectly fine. And then it happens at, probably happens at 4 point something, right? We could, of course, try and figure out where is that happening. .8, all right. So that's quite interesting. And there isn't any lamps or any indications or whatsoever here, but this one actually works when it comes to that output. So now I'll go back and see what happened to the other one. But anyway, I'll just clean these switches here and be done with that one. So I don't want to make this video a mile longer about all that. So here's how it works. You see 2 trimmers. The one to the very, very back, that is the output voltage adjustment. And then the one you see in the middle of the picture right there, it's impossible to photo. That is the current fold back point. And now I've adjusted it down to 3.8 or something. It's insanely critical. It's just 1/4 of a millimeter and it goes up and down a whole amp. So I don't know exactly how this one measures the current. I don't really see a current sense resistor or anything like that on this board. So that's really weird, but it is there, and now we'll play with it in the other. So I just want to share with you, I got a major breakthrough. I took out the entire readout display board, and I couldn't get this unit to 0 in the current readout. So this is current, and this is voltage. And now it works perfectly fine. So here's what I did. I was just adding more and more contact cleaner, and I was really working hard with those 2 switches, and it just didn't have any kind of effect. So it drove me mad. So when I took this out, I went to my outdoor shack with the compressed air, and then putting on more contact cleaner, so it's like completely wet, movie, and then compressed air to blow them clean. And now I got all the material blown out of it, creating some sort of a leakage. So that is really weird, but they really work now. And see, this LED isn't completely off. It's just not good. Oh, that's funny. Look at that. How's that possible? So I'll have to change that LED. But I think I finally fixed everything in this one. The last little detail I want to mention. Oh man, this is so funny. Here on the camera, this LED looks completely different from that one. How is that possible? Because I can't see this with my eyes. So that's something to do with the wavelengths or something? Weirdo thingy here. Cannot explain that. Okay, anyway. The idle power usage is at 0 volts, only 10 watts. But if I crank up the voltage on both of them, idle power is now 19 watts. And there's, of course, 2 reasons for this. First of all, now we activate both of the relays in each side, so there will be 4 relays activated. And also we got discharge resistors on the output and the drive circuits and all that, so it uses a little bit more idle. So I think that is what I wanted to show you about this fantastic unit, and that is definitely working perfectly fine now after a little bit of cleaning and fixing. And I really like the idea with the little lines here. You see, not super easy to see where you are. I mean, I just pick them in the middle here. They are about 14 volts, and you can easily see, okay, is it high or is it low? I mean, oh yeah, you see the clicks? it changes. There are, of course, 4 voltage ranges from 0 to 7.5, and of course from 7.5 to 15. And then the next one is 21.8, and the last goes from 21.8 all the way to the 30 volts of outputs. So that will be the 4 voltage ranges.